So a little bit of this is notation, but the big concept here is that we're trying to look at small differences and see where what difference the small difference makes in a calculated value. Okay, so this isn't perfect. This is probably as good as the linearizations in that it's really good when you have small errors. If you have big errors, it's not so useful. All right, so if we look graphically at what's happening, if we have this delta x value where we go from a to a plus delta x, so we're increasing the x value. The y value will increase as delta y. We'll take the higher value, f at a plus delta x minus f at a. That's that difference there. And so what we're going to do with the differential element is that we're going to take the derivative at a, and then, just like we did with the linearization, look at this line. And so we're going to get this little differential dy. And notice that it's not the same thing as delta y. Delta y is the exact value. Dy is going to be our estimated value. And that goes a little counterintuitive, right? Because when we were looking at the definition of a derivative, we were taking the limit as this little delta increment goes to 0, and then we got this differential element. But now what we're doing is we're expanding the concept of this differential element dx using the slope, which is really the slope of a line that's tangent to the curve at a. So dy is necessarily different than delta y. And of course, that slope is the derivative calculated at a. Okay, so what we're going to do is we're going to use dy to estimate delta y. And so if we're taking this approach, what we're saying is that if we're really looking for what is this value, this new value once we've increased a to a plus delta x, we're going to say, okay, that's going to be what our value was plus the differential. So it's no coincidence that this is exactly in the same chapter as our linearizations, because it really is more or less a consequence of that. Okay, so we want to look at small differences, not big differences. Okay, so an example right out of last semester. This one just deals with a polynomial function, just to kind of remind you how it's set up before we get into a trigonometric function. Okay, so we're looking at the radius of a circle being measured at 30 centimeters. The measurement error is 0.2 of a centimeter. What's the possible error in calculating the area? Okay, so you have this little error that's possible in the radius, but remember that the area is calculated with the radius squared. So we know that we can make a pretty good guess that the error in the area is going to go up faster than the area or than the distance of the radius. And so we look at our primary relationship here, area equals pi r squared, and we calculate, okay, if I want to see the difference that it makes in the area, I'm going to take the derivative of this. And so that's my differential element, but I'm going to use the chain rule to calculate what my dr is, because I have that. So I have 2 pi r dr. Now this tells you two things. Number one is it tells you, what the impact of dr is, but also notice that we have an r in there. So the rate of error, or the error that you're going to have in the area of a circle, depends on the size of the circle. So think about, if you have a really, really big circle and you have a measurement error, the error on that is going to be very, very different than if you have a very small circle with the same difference in the measurement of the radius. Okay, so we set r equals 30, dr equals 0.2, insert it into our equations, and so it's going to make a difference of potentially 37.7 centimeters squared. The area, if we look at it, is 2,827 square centimeters. And so here we have these terms again. The absolute error is just the error in itself. It has the units of whatever we're measuring. The relative error is the ratio between the absolute error and what we're measuring. And then ultimately the percentage error, which is the one I'll probably be dealing with the most, is what percentage. So it's just basically taking the relative error and multiplying it by 100 to get a percent. Okay, so we're interested in what kind of effect this has. And so if you notice, you have a slightly less than a 1% error in your measurement gives you somewhat more than 1% error in your calculated value. And this is really important when you're designing something or setting some experiment or something. The things that you can't control exactly, or the things that you don't measure exactly, is the error going to make your measurement meaningless, or is there a way that you can minimize your error by finding some relationship that maybe a 2% error in measurement only gives you a plus or minus 1% calculated measure. So this gets into a little bit of engineering, which I know most of you aren't going to study, but nevertheless still in experimental design and in biology and biotechnology it comes in to play. So are you all up with me?
No.
Okay, so let's put this in the context now of something that we just been studying. We look at trigonometric functions. Now, the fact of the matter is when you're going to be measuring angles, you're going to be measuring them in degrees. Just about everything that I know of that measures angles measures in degrees. And just like on Wednesday when I made that mistake in terms of trying to calculate a linearization of a degree, we have to think in terms of whenever we have our angle, that we have to think in terms of radians. It's okay to calculate, trigonometric values right off their degrees, but if we end up with something like we had, let's say in the previous slide where we had RDR, whenever we take that angle and use it as some type of multiplying factor, it has to be in radians. Okay? All right, so we're going to be dealing with some mixed cases here, and it's important to keep them straight. So what is the error and percentage error in computing the length of the hypotenuse? Okay, so we have this triangle 20 centimeters high, and the opposite angle is 30 degrees with possible error of one degree. All right, so how do we do this? First, draw a diagram and write our relationship. So we know that the sine of theta is going to be 20 over the hypotenuse. Now we're interested in the hypotenuse, so we're actually going to transform this into 20 over the sine of theta. So really we're looking for dH, right? The differential of h. And so we got to take the derivative of this, and so it's 20 because that's just the coefficient. And then we have sine to the negative 1 power. So that's going to be, if we look at the derivative of that, that's going to be negative 1 over sine squared times the derivative of the sine, right, by the chain rule. And so here we have this expression. And so we can put all these things together. And so our angle is 30 degrees, which is pi over 6. The differential element is 1 degree. Now I'm going to change that into radians, because notice here I'm going to be multiplying this expression. I'm not going to evaluate a trigonometric function. I'm going to multiply it by an angular value, so you always want to use radians when you're doing this kind of thing. And so when I plug it in, I get h over 1/2, which is 40 centimeters. That's the length of h, right? That's from this equation. 20 divided by the sine of 30 degrees, so sine of 30 degrees is 1/2. So the hypotenuse is 40 centimeters. And then we calculate the differential element. And notice here I'm using mixed case because I can easily make that pi over 6 and pi over 6. It calculates out the same. We know what those values are, so it really doesn't make a difference. And so we have the error is negative 1.2 centimeters for 40, for an overall length of 40. So we have a 3% error. Okay, so let's look at the interpretation of this. We have, this is negative now, right? Now what does it mean? That means that if my angle gets bigger, that my calculation of the hypotenuse should be shorter. And think about if I make an extreme sketch on the board here. Well, I'd like to use a marker that writes. Okay, so in other words, if my angle is 30 here, and actually it should be more, so I'll just write 30 plus, you see that this hypotenuse is shorter than that hypotenuse. So that's what the error tells you, and it's important to know that that's the direction of your error. And so this comes out less frequently when you're dealing with polynomial expressions, but with exponential and trigonometric functions, especially trigonometric functions, it'll tell you which direction you're going to be. So if you overmeasure your angle, you're going to get a shorter hypotenuse. If you undermeasure your angle, you're going to get a longer hypotenuse. Okay? So there's some physical meaning there. And even though if we have 1 degree over 30, that's about a 3% error, right? 3.33. We only have a 3.02% error in our length. And so it's not too bad at this point. If you do it at other extremes, you can easily get a feel for when your angles are more extreme, like imagine the sine or the cosine getting close to 0, that when you're measuring 90 degrees, it really doesn't matter the angle so much because it's very, very close to 1 then. And so you're not going to have much error even with several degrees measurement. But if you're measuring nearly horizontal, okay, that means the cosine is 1 and the sine is very, very small. That means that that hypotenuse will change quite a bit in length depending on the angle that you measure, okay? Okay, so why don't you try this one now with the same setup. What percentage error in the area of the triangle do you get? Okay, so the basics of this, I'll draw it on the board, was that we have a 30-degree angle, and here we have 20 centimeter height, and we're measuring this 30 degrees with a possible error of 1%, or of 1 degree. How much is that going to affect our area now? So remember what I did on the slide before, just to kind of walk you through the process, and then I'll advance this again. But I came up with the basic relationships. There's the formula for my hypotenuse. Okay, and then I took the differential of that. So you'll need to come up with a formula for the area based on what you know. And you should know this. I mean, this is something with a little bit of thought you can get.
The symbol in front of 1 degrees, what does that
That's plus or minus. So I'm measuring it within 1 degree.
But didn't you do Oh, did you do the same thing in the last slide though? Like,
Not exactly. I'm looking at the area, percentage of area error, before I was looking at the percentage of hypotenuse area. Hypotenuse, not the area. So you have to establish what's the basic relationship of the area of the triangle given this angular measurement and the height of the triangle. Okay, so there's the solution. And we got one more to do. Carbon-14 dating. Pretty controversial thing. It was invented by a researcher at Cal. And carbon-14 is a very, very small part of the carbon mix in Earth. You probably have learned this in biology. It's I forget exactly what the percentage is, but the vast majority of carbon on Earth is carbon-12. Carbon-14 is this little trace element, but it's not stable. The Earth manufactures it, and as we eat things that grow up from the Earth, we keep the same level of carbon-14 in our body as the Earth in general. When our bodies die, we're no longer taking in carbon-14, so the carbon-14 decays, so you can tell by the ratio of how much carbon-14 you have left how long you've been dead. Okay? And so they've dated things like the Dead Sea Scrolls like this. Now, carbon-14 has a half-life of 5,730 years, so this is really actually a pretty useful time measure. It's hard, from an archaeological and a geological standpoint to decide what happened, if you're looking at like prehistoric man 10,000 years ago, you can look at their artifacts, do some carbon-14 dating, and then have a reasonably accurate feel for how old it is. Now, you can set it up, your function this way, where it's 1/2 times the ratio of time to 5730. That means if I have 5730 as my time in years, so this is 1/2 to the 1, that means I'll have 1/2 of the original amount in my sample. Okay, now one of the reasons why you see a lot of these things put in the exponential form, remember we had this kind of duality from the beginning when we were dealing with a lot of these exponential decay things, is that taking the derivative of this is very easy, while this one you have to always remember to take the log of 1/2, all right, when you're taking the derivative there. Okay, so let's say you have an artifact, you've measured it, it has 25% the normal amount of carbon-14 plus or minus 1%. How old is the artifact and how much error do you expect? Now, I'm not saying this is 1% of 25%. I'm saying you can measure this so you're anywhere from 24 to 26%. So it's percentage points, not percent in terms of the overall error. You know how you can kind of confuse percentages that way. So how old is the artifact and how much error do you expect? Okay, so we know this, and we're trying to find t. So the first thing that we do is we take the log of both sides, and then we divide by this coefficient, and we get this function here. So time equals negative 82266.6, the log of the ratios. So if you take the log of 0.5 times that, you're going to get exactly 5730 out of this equation. But this is the equation that we want to use. And so this is kind of the important part of this, is to get this into a form of the equation that you can take the differential. Okay, so let's look at this equation. I'm going to take the derivative of it, and then my time by inserting 0.25 here, so it's negative 8,266 times the log of 0.25. So my artifact looks like it's about 11,460 years old. And then if I plug in my 0.25 into the differential equation, I can find that I'm going to be off about 330 years if I do in fact have that, that percentage. Now, notice what the sign says here again. if I'm going to have an increase in the percentage, so let's say my percentage is in fact 26% rather than 25%, you would expect that the artifact is younger than this, right? And so you would actually subtract these years to see what the lower bound of the age is. Now, if you actually have 24% rather than 25% carbon-14, it would be the opposite sign of this, so you would in fact have something older. So if we look at the ratios here, we're within about 3%. So there is a band of error here. I don't know how accurately they can measure carbon-14. I don't think it's 1%. I think it's a little bit more than that because carbon-14 is so rare to begin with. So if it's 5 or 10%, you could have actually a century or two, or maybe even not a century or two, millennia, maybe 1,000 years or so possible error. So carbon-14 dating is really great, but it does have its limits.